Hey, we're back to explore another cool idea with exponents. We will see a visual of why this idea is true, and it's rarely shown in textbooks, or I don't see many explanations of it. So I think it's pretty cool to be able to do that. It's going to be a lot of fun. The skills required to be able to understand this concept in this video is to be able to simplify expressions like this, like letter A and B. Take some time if you need it right now. If you don't know or aren't quite sure, you should go back and review these topics. All right, so let's go. This should be pretty simple. All of these in the left side are multiplying the same base. The first thing that comes to mind. And the nice thing here on the right side, the radicals are also the same numbers inside. That's kind of cool. So keep that in mind. All right, when we multiply the same base, we can add their exponents. And we can say 7 to the 3 plus 8. That's the same as 7 to the 11th power. Same thing here. Notice the same pattern. So 9 to the 16th power, 9 to the 6 plus 10. This one right here cannot be simplified, so we will represent as 5 to the same base. Multiplication means we're going to write it as 8 plus x. Or if you wrote it as x plus 8, that's fine. And then this one here, same base. The exponents 1/2 and 1/2. What should we do with those exponents? Let's add them. 1/2 plus 1/2. That should be the same as 3 to the first. Which if you want to be even more specific, that's just 3, right? Look at that. That one was a special case because that one's going to be powerful for what we're doing today. All right, cool. Next thing is, do you remember how to simplify these radicals? Now, yeah, I'm going to write it out one time, but it's not necessary to do this, all right? Hopefully you remember that, oh, that was pretty much the answers in front of us. But if you did think the long way and you multiply them, you say, oh, this is the same as radical 25, which is just 5. And that's what I'm saying. Look, the answer was right in front of us the whole time. So to skip this work, what do we know the square root of 8 times square root of 8 is going to simplify to? This is just going to be an 8. And what is square root of 4 times square root of 4? That's just 4. We should know that, right? And what is square root of 3 times square root of 3? It's 3. So that's the idea, all right? That's pretty cool. That gives us, and again, this is going to be also powerful for what we're doing. All right, so let's see if we can apply this in terms of area of squares. All right, so in terms of area of a square, here are 4 or 5 squares, and we are given the side length. Side length is 5 to the 3rd power. Side length is 3 to the 1/2, square root of 8, and so on. So one thing we know about squares is if we know this is 5 to the 3rd, what do we know about this side length on this side? It's also 5 to the 3rd. And what's 5 to the 3rd times 5 to the 3rd? We will say the area. And because the same base, we can add their exponents. It's 5 to the 6th. How did we get that? By adding 3 plus 3. Same idea for this one. Then we know that this is 7 to the 4th. And to find the area, we just multiply those or square them. We can say that area is 7 to the 8th power. All right. And again, if you want to see 2 ways of thinking about it, you can say, no, I'll write it one time, not for all of them. This was the area was 7 times to the 4th times 7 to the 4th, which is 7 to the 4 plus 4. That's one way of thinking about it. I just want to have you make connections to something we've done. Or you could have thought, this is 7 to the 4th squared. Notice 2 different ways of representing it. Is this going to be the same answer? Yes, it is. It's going to be 7 to the 8th. But we're also reinforcing what we know about exponents. 4 times 2, when we have a power to another power, we can multiply those exponents. It's 8. 4 times 2. And that's 7 to the 8th. Now that was just a little, not that we needed to do all this, it was just to reinforce what we learned before. And look how nice it is in this picture. All right, moving on. So I don't waste more time, but I don't think that was time wasted. This is 3 to the 1/2. We just went on a little tangent. All right, so here, then we think same base. We can say 3 to the 1/2 plus 1/2 is just 3 to the 1. So the area is 3 right here, right? It's just 3. And then we know that if this is radical 8, this is also radical 8. And the area must be 8. Square root of 10 has a matching side length of square root of 10. So the area is 10. So those ideas from above are now showing up in this geometry type of setup, which we will carry on to part 3. That's where the magic is going to happen, all right? So those people that tuned out, they're gonna miss out on on the best part of the show. Although I thought that was pretty cool. I didn't plan on doing this, but it just came out spontaneously, and I had fun doing it. But here's the best part of the show, all right? See if you want to try ahead and figure it out before I show it to you. To be honest, this is all I need to show you for you to figure it out. So if you're very observant and you look at for details and patterns, then you should be able to figure it out. And if not, let's check it together now. All right. So again, we know that if that's 5 to the 1/2 power, this is 5 to the 1/2 power. Therefore, what is the area inside the square? Can be represented as 5 to the first or just 5. That's good. Next one, if this is 13 to the 1/2, what do we know about this side length? It's also 13 to the 1/2. Therefore, the area is 13 to the first power, or just 13. And then same type of thinking here on the smaller one. If this is 7 to the 1/2, this is also 7 to the 1/2, right? Therefore, we know that this times this is 7 to the first, or just 7. I think I'm going to write them without the exponent of 1. It just looks better that way. That's the idea, right? Cool. Now, what happens when we have square root of 5, a square with a side length of square root of 5? That means that the other one is also square root of 5. And square root of 5 times square root of 5 is an area of 5. See if you're starting to see that strong connection. If this is square root of 7, this is square root of 7. Therefore, the area is 7. Okay. All right. And if this is square root of 13, this is square root of 13. Let me make that radical look better. There we go. That means the area is 13. And can we compare the left side, letter A, to letter B? What do you notice is happening there? Are they the same? Are they the same squares, or are they different squares? Let's look at them one by one. Is this square the same as this square right here? Yes, they must be, because what's true about their area? It's 5. Therefore, what do we know about the square with area 13? Look, if this one is the same as that one, it's the same square. And is this square the same as that square? Yes, because they have the same area. Therefore, what does it mean about this expression, 5 to the 1/2 and square root of 5? What does it mean about 13 to the 1/2 power and square root of 13? And likewise, what does it mean about 7 to the 1/2 compared to square root of 7? Is that they must be the same. So let's write that here. We're going to say that that's the key. That's the most important part of this idea, is that 5 to the 1/2, now we know that's the same as square root of 5. That's right there. For this one right here, we knew that, or let's write it down here. For 13 to the 1/2 is the same as square root of 13, right? This side length must be the same as that side length. And lastly, we can compare this little square to that square, and we know that, therefore, 7 to the 1/2 power must be the same as square root of 7. Look at that. That's pretty cool, right? And the nice thing is that we can extend this idea further. I won't be using geometry anymore, but we will be using this type of thinking. All right, so let's moving on to extend that idea. We have that example. If 7 to the 1/2 power is square root of 7, yep, the same statement, then what does it mean about all of these below? And guess what? Now we kind of have enough hints. I'll point them out to you so that we can do this very quickly in the future and not be intimidated by it. So let's point it out with color code. All right, I'm going to use blue and yellow. Let's use yellow to say, okay, how are these the same? The 7 is very visible here, but where are the 1 and the 2? The 1 and the 2 are hidden. They're implied, all right? So they're like the standard notation. Let's think of this one in yellow. Where is the only place that we can put a 1 and get a 7 in return? It is right here. Isn't 7 to the first the same as 7? Yup, that makes sense. And therefore, you may not know this, but there's always some number implied outside these radicals. And I'm going to write that in blue. When it's a square root, it's an implied 2. The 2 never needs to be written there. Oh, I don't know why I wrote that 3. It's 1/2. So there it is. There's the 7 to the 1/2. 7 to the 1/2. 7 to the 1/2. 7 to the 1/2. That's how it works. So when you see these fractions, they're called rational exponents. Remember that rational means a fraction. When you see these fractions, you should be thinking some form of a radical. And the base is 7, so that one doesn't change. But where does our numerator fall in this case? Oh, I think I switched the order. Notice how the 1 is still the same place as before. This is 7 to the first. And now this, whatever used to be a 2 is now a 3. So that's 7 to the 1/3. 7 to the 1/3 actually means cube root, if you're familiar with it. Once we get to cube roots and fourth roots, a number should always be written here. If it's a square root, it does not need to. So I'm going to go back and erase that one, or leave it there, but it's not required. If it's nothing written there, then by default, it is a square root. And I'm going to go away from color code and just go to my green. All right. So again, if you see a rational exponent, you should be thinking some form of a radical. What's the base? It is still 8. The numerator goes inside the radical. That's 8 to the first. And the fourth means the root. That means the fourth root. That goes outside. The fourth root of 8. This is saying, what's the fourth root of 8? That's one way you can read it, okay? What's the fourth root of 8? And then more advanced when it's no longer a 1 on the numerator. But the idea is the same thing. We see a radical. We see a fractional exponent or a rational exponent, and we write a radical. The base is still 6. What's the exponent? Is it 5 or is it 3? Be careful, the exponent is 5. And then I ask students, what's the root? The root is 3, all right? The root is 3. So 6 to the 5/3 is 6 to the 5/3, like that, 6 to the 5/3. That's one of the main ideas for this. And then again, if we see a fraction as an exponent, we can think, oh, it's just a radical. And x to the, this is a over b, all right? Not 9/6. X to the a over b. Which one is the exponent? Is it a or is it b? It's a, x to the a, and then b is the root. All right, like the 5th root or the 4th root or the square root or the cube root. Perfect. And if you understand this, then you can go back in reverse now, right? We're going to reverse the order. If we start with a radical and we're asked to write the exponent, then we just think some fraction. All right. So again, if you need a reminder, this is 1/2. If there's nothing there, it's implied 1/2. So therefore, this is 13 to the 1/2. Is there something written here? No, so we're going to put a 1, or it's implied. You can visualize it. You don't need to write it every time. And I think 15 to the 1/3. That's the idea. If we see this, it already has an exponent, but there's nothing outside. You can write it yourself if you need to see it. So you can see, oh, it's 3 to the 7/2, or 7/2. The whole fraction is the exponent, all right? Not just 7 or not just 2. The whole thing is the exponent. All right. And these are easier to visualize because they're already there in front of you. Now we can say, oh, this is just 5 to the 3/4. Be careful, not 4/3. Order matters in these. All right. And then lastly, this is x to the n power. So therefore we can write it as x to the n over m. I'll probably rewrite that. It looks a little confusing like that. X to the n, oh man. X to the n over m. There we go. That looks better. And yep, that's the main idea for these exponents that have fractions, otherwise known as rational exponents. Yeah, pretty cool idea. One of my favorites to teach. I hope you understood it, and let's keep moving forward. See you, and I always say see you, but I meant to say I hope you hear me in the next few videos. All right. Have a good rest of your day. Bye-bye.